To begin with, in mathematics as well as in terms of applications to economic problems or in other disciplines, linear functions are commonly used. These are simple to handle and lend themselves easily to algebraic manipulations. However, as one moves to advanced levels such as simplified or approximated functions, fail to capture the real scenario. In economics, a number of variables like cost, profit, utility are often quadratic in nature. It therefore becomes important to become familiar with tools capable of handling such functions. Quadratic forms are a special type of quadratic polynomials. The second order of optimization can be related to quadratic forms and their properties. After studying this module, you shall be able to know about the concept of quadratic forms, write quadratic forms in two or more variables algebraically and in terms of matrices, interpret second order differential as quadratic forms and relate to their properties, understand how to locate the sign of quadratic forms, understand and analyze quadratic forms with a linear constraint, relate these to second order conditions for optimization. Now we will be discussing about quadratic forms. Forms in mathematics refer to polynomial expressions where each term is of same degree. When the degree is 2, it is called as quadratic form. Quadratic forms are thus homogeneous polynomials of degree 2. Consider the following examples. Qx is equal to ax square. Qxy is equal to ax square plus bxy plus cy square. Qxyz is equal to ax square plus by square plus cz square plus dxy plus exz plus fyz. These represent quadratic forms in 1, 2 and 3 variables respectively. All terms in the functions above are of the same degree. Note that not all polynomial functions would represent a form. For example, consider a simple quadratic function in one variable. Y is equal to fx, which is equal to x square plus 4x plus 2. This represents a quadratic function but not a quadratic form. This is because of the presence of linear expression 4x plus 2. A quadratic form can also be defined in terms of matrices. If A is a symmetric matrix and X is a column vector of appropriate dimension, then X prime AX denotes a quadratic form. Quadratic forms in two variables. A quadratic form in two variables can be written as Qxy is equal to ax square plus 2bxy plus cy square, which is equal to x multiplied by a, b, b, c multiplied by x, y, y, which is equal to x prime ax, where x is equal to xy and a is equal to ab, bc. In general, the discriminant of a quadratic form is a symmetric determinant as the determinant of a matrix A above. Also, note that in Qxy above, fxx is equal to 2a, fyy is equal to 2c, and fxy is equal to fyx is equal to 2b. The Hessian of Qxy is thus given by h is equal to ab, bc multiplied by 2, which is equal to 2a. This implies that it is possible to write Q in terms of Hessian matrix. Since fxy is equal to fyx by Young's theorem, H will be symmetric. Qxy is equal to ax square plus 2bxy plus cy square is equal to half x prime hx. The knowledge of quadratic forms is greatly helpful in multivariate optimization problems for writing the second order conditions in a compact form and thereby verifying them easily. The second order total differential of function z is equal to fxy is a quadratic form in variables dx and dy and with partial derivatives as coefficients. D square z is equal to zxx dx square plus 2zxy dx dy plus zyy dy square, which is equal to dx zxx zxy zyx zyy dx dy. Thus, d square z is equal to x prime hx, where x is equal to dx dy is the vector of differentials and h is the Hessian matrix of the function fxy. Now we will discuss about the quadratic forms in more than two variables. A quadratic form in n variables is a function of the form q is equal to summation I is equal to 1 to n, summation j is equal to 1 to n, aij xi xj, which is equal to a11 x1 square plus a22 x2 square so on plus ann xn square plus a12 x1 x2 plus so on aij xi xj for all I and j. It can also be written in terms of matrices. Q is a function of x1 x2 till xn, which is equal to x prime ax, which is equal to half x prime hx, where A is an n cross n symmetric matrix, h is the Hessian of Q, and x is the vector of variables with n rows. A is equal to a11, a12, so on, a1n, a21, a22, so on till a2n, so on an1 till ann, and x is equal to x1, x2 till xn. In A, aij is equal to aji for all I and j. It is possible to write every given quadratic form in terms of matrices as above, with aij is equal to aii for I is equal to j, half multiplied by aij plus aji for I not equal to j. Example: Q is equal to 5x square plus 4y square plus z square plus w square plus 2xy plus 4zw plus 2xz plus 6yx represents a quadratic form in the variables x, y, z and w. Here matrix A is given by A is equal to 5, 4, 1, 0, 4, 4, 0, 0, 1, 0, 1, 2, 0, 0, 2, 1. Further, using a suitable orthogonal point transformation, any given quadratic form can be expressed as a diagonal form lambda 1 x1 square plus lambda 2 x2 square so on plus lambda n xn square is equal to x prime dx, where d has been used to represent the diagonalized matrix, with lambda 1 greater than or equal to lambda 2, which is greater than or equal to so on till lambda n, so that the corresponding symmetric matrix is a diagonal matrix given by lambda 1, lambda 2, so on till lambda n. The lambda i's represents the eigenvalues or characteristic roots of A. This formulation is helpful in determining the sign of quadratic forms. Now we will be discussing about the sign of a quadratic form. Just like any ordinary function, it is possible to determine whether a given quadratic form is positive, negative, or indefinite. A quadratic form Q is said to be positive or negative definite if for all points in the domain except at the origin. It is called positive or negative semi-definite if Q is greater than or 0 or Q is less than or 0 for all points in the domain. It is said to be indefinite if it takes a positive value for at least one point in the domain and a negative value for at least one other point in the domain of the function. Since the second order differential of any given function is a quadratic form, the negative or positive definiteness of a quadratic form can be related to the sufficient condition for existence of maximum or minimum value respectively. In some cases, it is obvious whether a given quadratic form is negative, positive, or indefinite. For instance, consider the following. fxy is equal to 2x square plus 9y square. This takes positive value for all xy except xy equal to 0, 0 and is therefore positive definite. By the same logic, fxy is equal to minus 2x square minus 9y square is negative definite. fxy is equal to x square minus 2y square is negative for 0, 1 and is positive for 1, 0. Thus, it is indefinite. The sign of all quadratic forms are not that obvious. For instance, consider 2x square minus 4xy plus y square, or say 3x square minus 25xy minus y square. Just by looking at the function, it will not be possible to tell the sign. If we can convert the given quadratic form into an expression such that the variables appear only in some squares, the definiteness of the sign will become evident. Consider Q is equal to ax square plus 2bxy plus cy square. This can be written as a multiplied by x square plus 2b upon a multiplied by xy plus b upon a y whole square minus b upon a y whole square plus cy square, which is equal to a x plus b upon a y square minus a b square upon a square multiplied by y square plus cy square, which is equal to a x plus by upon a whole square plus ac minus b square upon a multiplied by y square. Note that ac minus b square is equal to determinant of bc. Thus, q is greater than 0, which implies positive definite, which implies a is greater than 0 and determinant of bc is greater than 0. Q is less than 0 implies negative definite, which implies a is less than 0 and determinant of bc is greater than 0. Q is greater than or equal to 0 implies positive semi-definite, which implies a is greater than or equal to 0 and determinant of bc is greater than or equal to 0. Q is less than or equal to 0 implies negative semi-definite, which implies a is less than or equal to 0 and determinant of bc is greater than or equal to 0. Q is indefinite if determinant of bc is less than 0. Note that ac minus b square, that is, the discriminant of q, is required to be positive for both q greater than 0 and q less than 0, that is, the quadratic form being positive and negative definite respectively. Similarly, ac minus b square must be non-negative for the form to be semi-definite. Also, AC minus B square greater than 0 or greater than or equal to 0 implies A and C should be of the same sign. Further, note that fxx is equal to 2a, fyy is equal to 2c, and AC minus B square is equal to matrix ABBC, which is equal to half H, which is the Hessian. So the condition finally boils down to Q positive or negative definite if and only if fxx, fyy is greater than 0 or less than 0 and H is greater than 0. Q positive or negative semi-definite if and only if fxx, fyy is greater than or equal to 0 or less than or equal to 0 and H is greater than or equal to 0. Q indefinite if and only if H is less than 0. Now, determinant 2A is equal to 2A is the first leading principal minor of the determinant of H, and the second leading principal minor is H itself. So, Q is positive definite if and only if all leading principal minors are strictly positive. Q is negative definite if and only if the leading principal minors alternate in sign starting from being strictly negative. Indefinite if neither positive definite, negative definite or semi-definite, see below for semi-definite. All above criteria are clearly equivalent to each other and the choice may be made as per convenience as far as the bivariate quadratic forms are concerned. When we move to the multivariable case, the criteria involving the leading principal minor becomes handy. Now consider the function q is equal to 2x square minus 4xy plus y square. To illustrate these criteria for examining the definiteness of a given quadratic form. Here, a is equal to 2 positive, ac minus b square is equal to 2 minus 4 which is equal to minus 1, that is negative. So q is indefinite. In terms of partial derivatives, fxx is equal to 4 and fyy is equal to 2, both positive. H is equal to determinant of 4 minus 4 2, which is equal to 8 minus 16, which is equal to minus 8 less than 0. Hence H is negative, the given quadratic form is indefinite. Now considering the leading principal minors of H, the first principal minor is equal to 4 is positive, while the second principal minor of H is the determinant itself, so negative. This satisfies neither the requirement for positive definiteness or negative definiteness, so it is indefinite. The criteria for definiteness of quadratic forms extend to multivariate quadratic forms. For forms involving 3 variables, the Hessian will be third order, giving rise to 3 leading principal minors, say determinant d1, determinant d2 and determinant d3. Then it will be positive definite if determinant d1 is greater than 0, determinant d2 is greater than 0 and determinant d3 is greater than 0, that is all leading principal minors being positive. It will be negative definite if determinant d1 is less than 0, determinant d2 is greater than 0 and determinant d3 is less than 0. The odd numbered minors are negative and the even ones are positive. Thus, an n variable quadratic form will be positive definite if and only if di is greater than 0 for all I 1 to n, and will be negative definite if minus 1 raised the power I determinant di is greater than 0 for all I 1 to n. It may appear that if weak inequalities are used in place of strict inequalities, then the form in the question will be semi-definite, negative or positive as per the sign of the leading principal minus. This is however not correct. For example, consider a simple quadratic form in two variables, ox square plus oxy plus y square. It is clearly positive semi-definite, but here h is equal to 0, 0, 0, 2, so that determinant d1 is less than or equal to 0 and determinant d2 is greater than or equal to 0. Both are true with equality sign. It may thus be erroneous to conclude on semi-definite case. It can be shown that if the sign conditions with inequality is satisfied for all the principal minors and not just leading principal minors, then the quadratic form will be positive or negative semi-definite depending on whether the minors are all positive, greater than or equal to 0, or the alternative in sign as described. As the quadratic forms can be represented as x prime dx, where D the diagonal matrix with diagonal elements being the characteristic roots of A, and alternative criteria in terms of eigenvalues of the matrix may be given. The definiteness of any quadratic form Q, a function of xy, is equal to x prime ax is same as the definiteness of matrix A. The following general result comes handy. A given symmetric matrix A is positive or negative definite if and only if all eigenvalues of A are positive or negative semi-definite if and only if all eigenvalues of A are greater than or equal to 0 or less than or equal to 0. A is indefinite if and only if it has at least one positive and one negative eigenvalue. In economics, one often comes across problem of optimization involving one or more constraints. For example, maximizing utility subject to budget constraint or maximizing output subject to cost constraint. Such constraint optimization problems often involve linear constraints. The second order condition for given problems would involve quadratic forms where the variables are subjected to linear constraints. Consider the quadratic form qxy is equal to ax square plus 2bxy plus cy square subject to linear constraint pxy plus qy is equal to 0 where q is not equal to 0. Solving for y, this gives y is equal to minus pxy upon q. Substituting for y in q gives qxy is equal to ax square plus 2bx minus px upon q plus c minus px upon q the whole square, which is equal to x square upon q square whole multiplied by aq square minus 2bpq plus cp square. Now consider the determinant d is equal to determinant of 0 pq pab qbc. Expanding this yields minus a q square plus 2b pq minus c p square, which is equal to minus whole multiplied by a q square minus 2b pq plus cp square. Thus, qxy is equal to minus x square upon q square multiplied by d. This means that the sign of q would vary inversely with the sign of d. Note that the determinant d is the discriminant of the given quadratic form with a border placed to form the first row and the first column. This border is simply composed of 0 on the principal diagonal and the coefficients of x and y from the constraint forming the remaining two elements. This border discriminant is symmetric. The definiteness condition for Q can be stated in the form of this bordered discriminant. Q, a function of xy, is positive definite, negative definite, subject to px plus qy is equal to 0, which implies determinant qpq, pab, qbc is less than 0 or greater than 0. To take an example, consider qxy is equal to 2x square plus 3y square is equal to 7, where x minus y is equal to 3. Here determinant D is equal to determinant of 0, 1, minus 1, 1, 2, 0, minus 1, 0, 3, which is equal to minus 1 into 3 plus minus 1 into 2, which is equal to minus 3 minus 2, which is equal to minus 5, which is less than 0, implying Q to be positive definite. Qxy is equal to minus x square upon q square d, which is equal to 5x square upon minus 1 square, which is equal to 5x square, which is greater than 0. That is, Q subject to the given constraint is positive definite as it takes only strictly positive values for all possible values of the variables. For the n variable case, the conditions may be stated in terms of the leading principal minus of the bordered discriminant, the determinant D here. Say determinant D1, determinant D2, determinant D3, and so on. Note that the first leading principal minor D1 is always 0. An n variable quadratic form subject to linear constraint will be positive definite if and only if determinant Di is less than 0 for all I 2 to n, and will be negative definite if and only if determinant Di is greater than 0 for all I 2 to n. That is, all leading principal minors of the bordered discriminant should be negative for Q subject to linear constraint to be positive definite, and they alternate in sign starting with determinant D2 greater than 0 for it is to be negative definite. To apply it to the second order conditions of constraint optimization problems, consider the quadratic form to be the second order differential d square z of the function to be optimized and the constraint of the form gx dx plus gy dy is equal to 0. This is the first order differential of the constraint gxy is equal to c. Here, the variable of the quadratic form are the differentials dx and dy. The discriminant is the Hessian and the border has 0, together with the first order partials of the constraint. Thus, we have a bordered Hessian in place of bordered discriminant. D square z is positive definite, negative definite subject to dg equal to 0, implying determinant 0, gx, gy, gx, zxx, zxy, gy, zxy, zyy less than 0, greater than 0. These conditions extend to multivariate case as stated above, the discriminant being replaced by the Hessian. Let us now summarize what we have learnt in this module. Quadratic forms are homogeneous polynomials of degree 2. For example, x square plus y square plus 3xy. The quadratic form can also be defined in terms of matrices. If A is a symmetric matrix and X is a column vector of appropriate dimensions, then X prime AX denotes a quadratic form. This in turn is equal to half X prime HX, where H is the Hessian matrix. The second order total differential of function Z equal to, which is a function of X and Y,
is a quadratic form in variables dx and dy with partial derivatives as coefficients. In the matrix zxx, zxy, zyx and zyy multiplied by dx dy, d square z is equal to zxx dx square plus 2zxy dx dy plus zyy dy square, which is equal to dx dy, which is equal to x prime hx. A quadratic form in n variables is a function of the form summation I is equal to 1 to n, summation j is equal to 1 to n, q is equal to alpha ij, xi, xj is equal to alpha 1 1 x1 square plus alpha 2 2 x2 square, so on, plus alpha n n xn square plus alpha 1 to x1 x2 so on, plus alpha ij xi xj for all ij. It can also be written in terms of matrices. Q, which is a function of x1, x2 till xn, is equal to x prime ax, where A is a n cross n symmetric matrix and x is a column vector with n rows. A quadratic form Q is said to be positive or negative definite if Q is greater than 0 or Q is less than 0 for all points in the domain except at the origin. It is called as positive or negative semi-definite if Q is greater than or equal to 0, Q is less than or equal to 0 for all points in the domain. It is said to be indefinite if it takes a positive value for at least one point in the domain and a negative value for at least one point in the domain of the function. For a two variable case, Q positive or negative define if and only if fxx, fyy is greater than 0 or less than 0 and h is greater than 0. For semi-definite weak inequalities are used. It is indefinite if and only if h is less than 0. In case of n variables, the conditions are stated in form of leading principal minors of the Hessian matrix or the discriminant. Q is positive or negative definite if and only if all leading principal minors are strictly positive, alternative in sign starting from being strictly negative. It is indefinite if neither positive definite, negative definite or semi-definite. A given symmetric matrix A is positive or negative definite if and only if all eigenvalues of A are positive or negative, semi-definite if and only if all eigenvalues of A are greater than or equal to 0, less than or equal to 0, and A is indefinite if and only if it has at least one positive and one negative eigenvalues. An n variable quadratic form subject to a linear constraint will be positive definite if and only if all leading principal minors of bordered discriminant are negative, and positive definite and if and only if they alternate in sign starting with modulus of d2 greater than 0. Since second order differential of functions represent a quadratic form, it is possible to examine their sign with the help of conditions applicable to the quadratic forms.